Alright, let me turn all of this stuff off. Alright. And we should be good to begin. We should be live on YouTube and Twitch now. I guess we got Jake from Discord talking in the YouTube chat. Okay. So yeah, I figured I would make this exercises discussion type thing a little bit more open. So hopefully we get some YouTube people as well. And we have some questions that were in the Discord. I can start writing them on the board, a couple of them. Let me see. Go to the Discord real quick. Right, somebody put a lot of probability questions. Well, some probability questions, complex numbers. Oh, it looks like they might have edited it to make it look nicer, so that's good. Right. Oh, Jake had this first question. I thought this one was a decent one to go over. So square root of 2x plus 8 is equal to 5 log base 3 of x. And I think we had a problem similar to this the other week that Jake was right to point out that the solutions here can only be positive because logarithm, right, when we plug in x, it needs to be positive here. Can everybody see this? Yeah, I think we're good. I'm confused. Snake King, is that? I thought Jake was the other username, not Snake King. So this is Jake's problem from Discord. And I guess they give us some possible answers. So I'll just write those over here. Oh, also we'll be going for 2 hours today. So this is the start. 4 o'clock. I'll be going to 6. So just FYI for everyone who's tuning in. So A is a 105 possible answer. B is 350. Luckily, they're all positive, so there's no, well, I don't know, luckily or unluckily, I guess. Unlucky because we can't cross any answers out from the beginning. Right, it's 2.2. And 3.1. Oh, this is the one you were talking about, Jake, that you had the 2.2. You said, okay. Well, let's, I think Jake said the answer was 2.2. Let's try to show that. I would factor 2 out of 2x minus 8 to 2x plus 4. Okay. That might help. Sure, we can try that. So basically, and we can pull the square root of 2 out as well, right? Not sure if we needed to do this, but I don't think it hurts too much. Right, so seems like we want to just, maybe move the 5 to the other side, then do the inverse of taking a log base 3, which would be taking 3 to the power of this, right? But that's going to be kind of awkward here, right? So maybe is there something else we can try? Or maybe we can try to use some log rules. Let's see. Maybe try to square it. Let's see. I mean, we want the x alone somehow, so at some point we're probably going to need to do 3 to the power of something, right? Or 3 to the power of both sides, right? But it kind of gives us an awkward thing over here, right? Okay, we factored the 2 out. Square. There ain't no way of factoring x out of both sides. Yeah. Square it and try. Yeah, I mean, we can square it, but then I'm not sure what we're going to be doing with that side. Square it. Are you sure we're not supposed to be finding like some numerical solution here, Jake? Or to bring 5 up into its exponents? What do you mean by that? Let's see. Bring 5 up into its exponents. Use the power rule of log. Okay, yeah. Yeah, I mean, I think the power rule of log is probably the correct way to go, but, oh, okay, so you're 5 up into the exponent. Can't do 3 to the power on both sides. I can't see with this light here. They said solve for x. Okay. How are you getting log base 3 to the of x to the 5th? Oh, okay, I see what you're saying. Bring it into here. That's what you're saying? Yeah, all right. Yeah. Well, yeah, we can do that first, sure. Yeah, so we'll use that log rule, right? But I still don't see... Yeah, I mean, I don't really see how to get it without using some sort of numerical approximation method. But maybe I'm just missing something. I don't know. Does anybody in chat see how to do this? We could try to take 3 to the power of both sides, then we'll get like x to the 5th, 3 to some square root power with an x, and then it'll just be awkward again. I mean, it's not going to be a polynomial. Yeah, was there any hints in the Discord? I don't know. I didn't really read the problem too carefully. Let me see. Thought of converting the square root into 1/2. Yeah, I mean, that's probably a good way of viewing it. Like viewing the square root as a power to 1/2, to the 1/2 power. But, I mean, the fact that they're giving us a numerical answer here is also funky, but... guess that's okay. I mean, if it involves a log, then it's probably gonna be some weird decimal anyways. Snake King says I'd have tried to square it, but that leads nowhere. Yeah. I mean, that's what I was looking at. I was trying to square it, but then it didn't really go anywhere. So, of course, all these functions are differentiable. So if we wanted to approximate them, and internet, of course. All right, I think we're back. Yeah, of course, if we wanted to approximate an answer, we could always use something like, I think, Euler's method, like, or no, Euler's method is for differential equations, but I think there's another Euler method for, finding roots. Hopefully we're back. Connection lost. I don't know. Hold on. What is going on? Yeah, I crashed. I'm trying to see. This window is yeah, so you got to bear with me, guys. This is the first time I'm doing both. All right, I'm just going to make this bigger. There we go. Okay. I think I'm back. Yeah, should be back. Yeah, this internet in my house is just they're just not fixing it. So, I don't know what to do about it. Stream alert, 2 stream alerts. Okay, great. How do I make this turn off? All right, there we go. Okay, I think we're back. People, yeah, Twitch crashed. We're still trying to solve this problem. Now there's like a slightly longer delay. I gotta fix this delay too, but all right. Well, I think we'll be stuck with it for now, but Lambert W. Yeah, I mean, it's possible that you need some weird function to solve this, right? You can't hear me at all? Delay too, but can you guys hear me now? Yeah, I think it's working again. I'm just trying to make sure that the audio is working. Okay, I think we're back. Oops. Yeah, everything is working very funky on this. What did it just do? Now it added the window I just had, and it moved it inside of the, what the? Yeah, OBS is being very weird to me. Okay, yeah, it moved this window to like something I wasn't trying to do at all. Okay. Yeah, what the is wrong with this thing? All right. Yeah, OBS just being very annoying. Wow. This is crazy. Can I just close this? Okay. Oh, okay, audio's good, great. Sorry about this. Alright, I closed one of the windows that I probably need. Okay. Stats, stream information, restream channels. Can this work, please? Thank you. Yeah, OBS is not liking me right now. Okay. Yeah, Jake. Other people say they can hear me though. So I don't know what to tell you. You can't hear me from YouTube. Okay. Now it says it's offline? Huh. Alright, I'm just gonna try to make sure everything's working properly. Alright, it says Twitch is online. You go to YouTube. Okay, YouTube's online. Okay, I hear audio on both. Yeah, I hear it, so should be good. Yeah, try to refresh the page if it's not working right now. If you're on YouTube or Twitch, either or. Try to refresh the page and we'll start back up again. But yeah, yeah, I'm not so sure about this problem. I mean, if you need some sort of W function, like some sort of weird analytic function, then, I mean, I don't know how I'm gonna get this answer from that. If there's another way to do it, I'm all open to hearing the answer, but I don't see how to do it from here. Because we can raise 3 to the power of both sides. We're gonna get x to the 5th equals 3 to some, you know, and then we're gonna have this in the exponent. I don't think that works. I'm open to some suggestions. So how do we show that this is 2.2? I don't see it. First identity. 3 to a power. Yeah, I don't see it. Plug and check. Yeah, I mean, Jake, do you have any hints for us? This is your problem. So, I mean, I don't see how to do it. Obviously, we can find a numerical approximation that will be near 2.2 if that's the actual answer. And is it exactly 2.2? Because somehow I doubt it's like exactly 2.2, right? Maybe it is, but 2.2 seems like if I plug 2.2 in here, like this is definitely irrational, right? And then, I mean, I don't know how this is going to be equal to that. Maybe it is. I'm not getting anything from the audience here, any help, and I'm not getting any help from Jake. So I don't know where to go with this problem. We know how to do it numerically, right? We can always, if we have differentiable functions here, you know, we can use some sort of differentiable methods to approximate the zeros. I can just take this, subtract this, and, you know, try to find zeros of that using the derivative, right? Do that. What, find the approximation? I mean, we need a computer, though. I need a calculator. I can't do it by hand. Well, we can calculate, like, you know, a couple iterations of the approximation, but I think that's kind of like probably not the point of the problem, but I'm not sure. Maybe we could divide by 5. Yeah, I mean, we can divide by 5, but I think we're still in the same problem, right? Same issue here. Yeah, we can divide by 5. So it's like square root of 2 over 5 times square root of x plus 4 is log base 3 of x, but yeah. I think the point of this problem, which Jake is probably leaving out, is that they want you to graph both sides and then use that information to try to estimate this. But of course, I don't think Jake gave us the full information of the problem, which seems to be a running theme with Jake giving us these problems, not giving us enough information, Jake. So please, if you can give us enough information to actually solve the problem, that would be helpful. Yeah, so somebody in chat says Lambert W doesn't even work here, so that's also possible. Rex is saying. So yeah, someone in chat says I get x equals 2.16279. Yeah, which would round to 2.2, right? Use the definition of a logarithm to say 3 to the power of whatever is there divided by 5 is equal to x. Wait, what? Is the definition of a logarithm to say 3 to the power of whatever is there divided by 5 is equal to x. Yeah, I mean, yeah, that's kind of where we're going with this, but I don't think that helps us solve the problem. We're kind of just rearranging symbols, right? I mean, that's kind of the way you would want to approach this, but I just don't. The more you solve for x here, the more convoluted you're making this side, and then I don't think there's a way to fix it. You're always kind of like having to go back and forth between solving for x here and then you want to solve for x here, but every time you try to solve for x here, you make this side more complicated. And every time you try to solve for x here, you make this side more complicated. So, I'm guessing that the problem from Jake is to use like a graphing calculator or something, graph both functions, and then find maybe where they intersect. It said solve this equation. I mean, especially because we have like possible answers here. I'm guessing that's what you want to do. So you'll probably like graph both functions. There'll be two different curves here, something like that, and they'll, you know, they intersect at some x value. So one way is you can use a graphing calculator, but I think the graphing calculator is probably using some sort of calculus in the background. So you could also use that. I think, what is it? Is it called Newton's method? It's not Euler's method, right? That's the differential approximation, right? But I think it's Newton. Is it Newton's method, chat? So you could basically use Newton's method with this minus this, and you're approximating roots. And if you know, I guess you could like plug in different values that are near these, and then see if any of those are attractors for the approximation. But yeah, you have root finding methods, or you have a calculator method, which is probably using some sort of root finding algorithm as well. Okay, so Jake, are you still here? Can we move on from this one? I don't know. Is that a satisfactory answer? So I'm guessing you said the answer was 2.2, and you gave us a picture of the graph that looked sort of like this. So I think that's what you were supposed to do. But I don't think I can do that by hand. I mean, we could do a couple iterations of the approximation, but that's it. Likely won't work now that I think it. Yeah, Snake King, I don't think that works. Alright, let's move to a different problem then, I guess. Alright, any problems from the audience that we want to go over, or else I will start picking at these ones from the Discord. So we got that snake JNDR submitted a few problems. I think the complex analysis one I can definitely go over immediately, and then I'll probably get stuck on the other ones for the next hour and a half. But oh, and then we have Rex's problem as well. Yeah. So what do we want to go over? Probability. Let's see. Yeah, just move on. I'll give you a new one. It's easier. Well, I don't think this problem is hard. I mean, you haven't told me how you did it. If it's easy, then tell us how to find the answer. It's not that it's hard. You just need a calculator to do it. I mean, it's very easy with a calculator. I would say this is an easy problem, not a hard problem. As long as you have a calculator, then it's super simple. Snake King, this is all the probabilities ones? I think it's confusing because we have a Jake and we have a Snake, and I'm not sure. I think they're two different people, right? Let's just go over this complex numbers one first. I think this one's I don't want to waste too much time. But we are doing 2 hours today, so no big deal if we go a little bit slow. We are on YouTube and Twitch for the first time if people are tuning in. I just graphed it. Yeah, if you graph it, then, I mean, that's all you... If you have a graphing calculator, there's a setting. I don't have one in front of me, so I haven't done it in many years, but there should be a way to either find roots or you can check about intersections between two different functions on the calculator. But, of course, what the calculator is doing in the background is it's just using some calculus to estimate either the intersection or the roots of, whatever function or functions you're looking at. Okay, yeah, Snake King says I'm that snake JNDR. Yeah, okay. Yeah, I like these problems. So I'm just going to go over this complex numbers one first because I think it's kind of simple and I can explain it really quickly, and then we can go on to some of the more complicated ones. So this is task 18. This is in the Wednesday submissions. Task 18, complex numbers. And the problem is we have two complex numbers, Z1 and Z2. So Z1, Z2 are complex numbers. And they are roots of the equation Z squared equals -I. So basically they're like the complex plus or minus square root of -I, but then you need a little bit of care to, you need to be a little bit careful about what that means. Then it says, in which Gaussian complex plane plot are these roots correctly displayed? So I'll just summarize this by saying, in which plane are the roots correctly displayed? Or in which quadrant, I guess, or... Yeah, in which plane plot are they correctly displayed? So in which picture are they? Correctly displayed. All right, and then I'll draw them in a second. What do we have in chat? You should do all the other ones first because I've only joined a few days ago. I feel like the people who have been here longer just... No, don't worry about it, Jake. I mean, you put these problems in. I asked for problems, and these are good problems, so don't worry about it. Impossibility and complexity are different concepts. Try to solve 1 = 0. It's not hard. Yeah. I mean, of course we can come up with problems that you can't solve by hand because there is no... I mean, there may only be a numerical solution to that answer. Like, there may not be a nice closed form decimal answer or something, or fraction, or, etc. So you might need the computer to do it, or you might need some equivalent method, which is some, numerical approximation method, which either you would have to do by hand or you would need a computer to do it, right? Okay, so let's draw some of these pictures. So it says A, B, C, or D. A looks like this. So Z1 is here. Z2 is here. And they kind of don't give us numbers other than that, like 1 is over here. B is, they're kind of like this. So this is now Z1, I guess, and this is Z2. Or C, they're both on this side of the plane. Z1 over here, Z2 over here. Or I guess D is the final possibility. Multiple choice, and they're in this one, they're like on opposite sides on this plane. Okay, so what do we think the answer is? A, B, C, or D? The roots of z squared equals negative I. And I can already tell you I can knock out 2 answers already. Because if you have a square root of a number, there's always going to be a plus or minus answer. So only some of these graphs represent plus or minus. Actually, no, I can only knock out one of them. So which one can we eliminate immediately just because of the way this equation looks? Oops, sorry, I'm standing in the way. Let me get another marker here. Okay, so A, B, C, or D. And we're looking for the roots of, or the plus or minus square root of negative I. And negative I would be, I guess negative I is Z2 itself right here. So we want the plus or minus square root of this. And we need to think about, how do square roots work in the complex plane? How does multiplication work in the complex plane? Right? So that's all the types of things you're thinking about that go into, trying to solve this question. Okay, so Rex says C. Hey Rex, can we do polls here? Is that something that a mod can do? Maybe we could try to just one as a test run. I don't know if it's easy or not. Or no, maybe if it's too hard. I don't want you to waste too much time doing it. Okay, so stream's working on here. I'm just checking the streams to make sure everything is still working. Alright, seems to be okay. Snake King, you say I do not know? Are you talking about A, B, C, or D here? So Rex, Rex, you're saying C we can throw out, right? Yeah, C is the one I think we can throw out, right? Right, because if it's going to be a plus or minus square root of a number, that means that one of the answers is going to be correct, and then the minus of the solution is also going to be correct, right? So the Z2 is not the minus of Z1, so these are not negatives of each other, right? In this, it looks like they're drawing complex conjugates. So C is definitely the one we know is not correct. Hello. The wave. I think also math streams might be hard because it's like if I give you guys time to think, then it's like dead air. I'm not talking, right? So then people get bored. I have to be somehow more entertaining, but I can't entertain you while you're thinking about math, right? So I don't know. It's got to be some balance, maybe. So how, if no one, I can do a poll on Twitch. Yeah, we could try it. I mean, if it's easy. So we know C is not the solution, right? So do we think it's A, B, or D? And we want the roots of this, like z squared plus I equals 0. We want the roots of that, or we want the plus or minus square root of negative I. We can think of it both ways. So what are you teaching? Well, I'm not really teaching today. We're just going over some exercises. So this one's on complex numbers. We did, find the roots of this equation for the last one. Just kind of going through maybe some probability questions next, but really it's kind of open to the viewers, whatever they want to go over, then we'll go over it. So the angle is pi over 2, right? For negative I, it would be like negative pi over 2, right? So remember the angles for complex numbers, we're going to view them as angles from this positive real plane, and we're going to go counterclockwise. So you would have to go all the way around. It's actually kind of like 3 pi over 2 radians, or negative pi over 2. Would be cool addition, actually. I'm not sure what you mean by that. Oh, you can do a... Are you talking about the poll? No one's even guessing. Well, I think, Rex, I think you were saying that C is not correct, right? You said C, but I think you meant that C is not correct. And we can kind of see why it can't work, because Z1, if we square Z1, we're going to get something that's, positive imaginary, right? Z2, the square root of the square of Z2 does look like it's negative I, but Z1 doesn't work. And like I was saying, we know it's not correct because they need to be negatives of each other. Voting is at the top of the chat. Oh, okay. Yeah, I guess I can't see it on this restream chat. That's probably what the problem is. So D1. Okay. So people in chat think it's D. Right. D sort of, well, we know we just said Z2 works. So that seems to be good. And then if we square Z1, well, also we know that if we have one root, the other root needs to be the negative. Yeah. So I think D works. D sounds good. Good job, chat. Yeah, C is conjugates, so we know C doesn't work. They need to be negatives of each other, because if we have one solution of this, then the negative is also a solution, since squaring kind of kills the negative. Negative 1 times negative 1 is just 1. So if we know what one root is, then we know the other root is the negative of the other one. So we know they can't be conjugates. This could be an answer, but then neither of these is a solution. Like if we square either of these, we get something that's either positive here or positive here. In fact, I think these are the square roots of positive I. And then if we square these, we get like negative 1 for both of them. So this doesn't work either. So D has to be the solution. Okay, so the wave says, can I ask about how you would solve a certain integral, like for example, integral, okay. Yeah, we can look at an integral. So I just did some other people's problems. So let me look at this integral for a second. I think these are kind of ugly though, right? I'm trying to remember how to do this. Yeah, I might. You guys might need to help me with this one, but I'll give it a shot. So this integral 1 over x squared plus a squared. X squared plus a squared. To the 3/2. Like that. Yeah, so antiderivative. Yeah, we'll go back to more of those ones. We'll do more of those ones, Snake, in a second. We're just gonna look at this, try to find the antiderivative. I remember that when we have some problem like this, x squared plus a squared, we're probably gonna think some sort of trig substitution, I believe. We want this bottom part to basically just be like a single thing squared. So then the square and the over 2 will cancel. X squared plus a squared. Is this the one that's tangent squared? Tangent squared plus 1 is like secant squared, I think. So we just need to remember all of our trig identities, basically. Let's try to write down some of them. So we know that sine squared plus cosine squared is 1. We know that, what else might we need? So we can always find the other ones from this by like dividing by sine squared or something, right? So 1 plus secant squared is cosecant squared, I believe, right? Or not secant, I mean this is, what do they call it, cotangent? And then also if we divide by cosine squared, then we get tangent squared theta plus 1 is secant squared. Okay, so where are we at here, chat? So which one of these identities will I probably need? I think these are like the 3 main ones. Maybe you can come up with some other ones, but I think these are the 3 that are used the most. So basically the idea is we want something to change. We want to be able to change this bottom part into like just something squared. So probably maybe one of these two, but then I don't know which one do we want. Probably we want to choose the one where the dx is going to be like simplest, I guess. Or wait, maybe I'm confusing myself. I think we want some sort of trig substitution though, right? So probably x is going to be like some tangent squared or something, or cotangent squared. Well, I guess that only works if a is 1, right? Huh. So yeah, if a is not 1, then I think I'm still need to be careful. Yeah, these integral ones with the substitutions can be pretty hard. Unless you know the trick, and then if you know the trick, it's not that bad. But I probably know the trick, and I probably forgot, so. X equals, oh, okay, right. So yeah, some of them, and then there's the hyperbolic relations as well. So, okay. Yeah, that one I'm probably not going to be able to remember. So, okay, so they're saying use the solution x equals a times hyperbolic sine of u. Okay, so we can think about that for a second. Yeah, so I think there's very similar relations. Is it for hyperbolic? I think it's like hyperbolic sine squared. Let's just say need a letter. R. I don't know. Is it minus? Is one? I think there's some sort of similar relation like that, but then. And then you can derive another one by dividing by sine h. You get, all the hyperbolic ones. Okay, so the person in chat is saying we can do a substitution x equals a sine hyperbolic sine of u. So dx, I think, is like a hyperbolic sine cosine of u. I got no clue where brought the sine u from. Sine cosine. Yeah, same as sine cosine. Yeah, the only difference is if you take the derivative of hyperbolic cosine, it's not the negative. You just get back to the original hyperbolic sine, I believe. But I'm not too refreshed on my hyperbolic sine trig functions, to be honest. I don't use them basically ever. Okay. So then, so if x is this, then there should be another relation here. Oh, right, yeah, right. Then you can factor out an a squared on the bottom. Right, and then hyperbolic sine plus 1. Plus 1. Am I remembering this wrong? So yeah, I mean, we can do this substitution here, but then I'm going to get a hyperbolic sine squared. So I'll factor in a squared, to the 3 over 2, whatever. So I'll have x squared, or I'll have hyperbolic sine of u squared plus 1. But that's not the identity I have here, so I need a different identity. But do I have this backwards? Maybe it's the other way. Yeah, if this is the other way, then I can just move this to the other side. No, then that would be, yeah. Yeah, maybe this is backwards. I'll look it up real quick, but hyperbolic sines, you guys are hitting me with the, okay, hyperbolic sine identities. Hyperbolic function identities. Oh, okay, yeah, I do have it backwards. Okay, it's hyperbolic cosine squared minus hyperbolic sine is 1. Okay, then we're good. Yep, should have known it was backwards. There's 1. Right, now we can move the sine squared over to one side, so we get 1 plus sine squared u, or hyperbolic sine squared u is hyperbolic cosine squared u, and then so this bottom part is going to become hyperbolic cosine squared of u, but then we have the, yeah. Okay, I think we're good now. Probably need to kill this marker at some point. Okay. Yeah, I figured it out. Okay. So you rearrange it. Now we're going to do the replacement here. So this is, or we're going to substitute, right, for x. So on the bottom, we get an a squared hyperbolic sine squared. Oops. I'm so used to writing just sine squared. Hyperbolic sine squared of u plus a squared to the 3/2. Yeah, then we can factor out this a squared here. So this is just going to be like a 1 over a squared to the 3/2. So the squares will cancel, just be a to the 3rd, I think. Yeah. And then integrate 1 over sine squared u plus 1, but sine squared u plus 1 is cosine. Oh, I forgot the, yeah, this, well, it is, yeah, I guess it is still dx, so I'll plug it in this time. Okay, so hyperbolic cosine squared 8 of u to the 3/2, and then dx is actually a hyperbolic cosine of u. du, forgot the du here. The main question, to be honest, is how do you even come up with the hyperbolic substitutions? I can get the trig substitutions, but the hyperbolic seems kind of out of the blue. Well, I mean, they're not, I mean, they're all, if you know the trig substitutions, I feel like they're equally as weird. Like, it's either sine squared plus cosine squared is 1, or you have this cosine hyperbolic cosine squared minus hyperbolic sine squared equals 1. But either way, I mean, they're all for different, there's different permutations of this problem, right? Like you can have x squared minus a squared, then you might need a different trig identity. Or basically all of the different relations here. You're going to need one of these, either trig identities or hyperbolic trig identities. But they all have, you'll if you do more of these, you'll see that they have similar, the way that they look. Like right when I saw the problem, when you gave it to me, I immediately thought trig or hyperbolic trig, something like that, right? We needed one of those identities. We just need to figure out which one. Normally a problem will have solutions in many different forms. Yeah, sometimes. Right, so are we almost done here? So then the 3/2, so we have squared to the 3/2, so this just becomes cubed on the bottom. So this is like a hyperbolic cubed here, right? I guess we can just erase that. And then cosine hyperbolic u, cosine hu, one of these cancels, right? So this is just squared, instead of having to rewrite everything. One of these a's cancels. So we get a squared on the bottom. So now it's just an integral of 1 over hyperbolic cosine u squared. Now, how do we solve this? What is this, like an integration by parts now? They got to make it even more hard for us. Oh, I can use tan? Oh, you're saying there's more than one of it. Oh, I see what you're saying, Rex. So you're saying tan here works as well, right? Oh, I see. Yeah, some of these are weird. Some of these you can actually do them 2 different substitutions. You can actually get the same answer. Or sometimes it's annoying, you'll actually get, it will technically be the same answer, but it will be written in 2 different forms. So you'll actually be, technically you'll be looking at like some trig identity. Or they differ by some trig identity. But yeah, this one's annoying because I'm not sure how to anti-differentiate this. So maybe we do need to use Rex's method. Unless, of course, maybe you can do this by integration by parts or something. I don't know what the integral or the derivative of, well, I know that the derivative of cosine h of u is sine h of u, or, hyperbolic sine. But, yeah, does anybody know what the antiderivative of, I mean, we basically simplified the problem. Now it's just, we need the antiderivative of this, but I don't know what that is either. So basically we're just utilizing the relations of a squared plus or minus b squared equals 1. Yeah, so you'll either get trig or hyperbolic, or sometimes you can use the other identities that you can get, like the ones with tangent and cotangent, or the ones with I think it's tangent and cosecant, and then the other one has secant and cotangent in it, or do I have it backwards? Yeah, of course you can always figure them out. I just write it out every time I do the problem, just so I don't have to memorize it basically. But yeah, just write out all your identities. Try to figure out which one you can use. Probably you want to practice these though, because like if you're gonna do it this way, maybe I don't know what the antiderivative of this is, so maybe that's not the right way to do it when you're doing it on a test, or maybe you can figure out what the antiderivative of this is, and then you're fine. But probably the substitution that Rex is saying, Rex, does this work better with tan? So if we try to do this something similar with tangent, so x equals like a tangent u or something, right? Then dx would be like a, I think it's what, secant squared? Derivative of tangent secant squared. Or is it the secant tangent one? No, I think it's secant squared, right? Du. Then that's going to give us, what, something with regular trig functions, I guess, which we know how to find the integral of. I don't want to erase this yet. Can we find the solution from here? Or is this like a dead end? I mean, as long as we know what the antiderivative of this, then we're done, right? But something tells me maybe there's like a, is there a hyperbolic half angle formula or something? Then we can, or a double angle formula or something? Yeah, no problem. Can someone type this into Wolfram? I'm just curious. Does this give us anything that's like intelligible? Or should we just do the other substitution that Rex is saying with the x equals a tangent u, and then use the other identity, the other trig identity? I do sort of recall doing these like in high school or something, and remembering that you could technically use two different identities for some of these. I had tunnel vision on the trig only, and it came out super ugly. I've not taken integrals yet, and I can safely say I am not going to like them. We got integration tables and all, to be honest. Yeah, but I don't know if this one's in the integration table. I have a feeling it's not. I mean, if it is, then, you know, obviously do it this way. But yeah, I'm just curious if anyone's can plug this into Wolfram, or I guess I can plug it into Wolfram as well. It's the derivative of, oh, okay. Oh, right, because this is, I see. Yeah, because this is, remember we have like, you know, similar to the derivative of tangent is secant squared, right? Or do I have this one wrong too? But yeah, that makes sense, okay. So it's the derivative of the hyperbolic tangent of u, okay. So yeah, I guess if you have your tables, then you're good. Yeah. If you just, or if you memorize this, then you're also good. So, hyperbolic tangent, right? Interesting. Okay. Or no, okay. Oops. Not integral. So, hyperbolic tangent of u, I guess plus c. Plus some constant. And then we could plug back in x here. Yeah, there's going to be some sort of like hyperbolic. It's going to be ugly. I mean, yeah, there's like a hyperbolic Pythagorean theorem here. And you're going to have like the... Yeah, you're going to have to solve back for u here, right? To plug in, to get everything in terms of x. But then you're going to have like a hyperbolic tangent of a, you know, an arc hyperbolic sine function, right? So you remember when we have these, like, we're plugging in an inverse trig function into a normal trig function, and then there's like a way to use the Pythagorean theorem to get the solution. So yeah, I mean, this technically probably works, but it's going to give you a very ugly solution that your teacher's probably going to yell at you for and tell you to go back and do it a different way. Who are you talking about, Rex? So yeah, personally, I would say that this is probably not the correct way to do it, even though, I mean, the answer that you get at the end is probably technically correct. So yeah, let's try to do it the other way. I guess, yeah, so the final answer would be like 1 over a squared hyperbolic tangent of the arc hyperbolic sine of x over a, and then plus some constant. But then you would have, to use some sort of relation to maybe rewrite this composition. But let's try to do it the other way. Big man in their crimson sweater. Yeah. Let's try the other substitution here. Let's see if it comes out a little bit nicer, maybe. So this technically probably does work, but doesn't give us a pretty solution. We got to get the nice solution, right? We got to do it the most aesthetically pleasing way possible. All right, so let's try this substitution. So also, can you guys check that I did this derivative right? So derivative of tangent is secant squared. Is that correct? And then, so this guy is going to be 1 over, yeah, so I'll just pull the 1, we'll pull the 1 over a cubed out again. So it's going to be tangent squared u plus 1 to the 3/2 dx, which is now a secant squared u du. Oh, we're dropping frames. No, we're still good, I think. Oh, no, something went offline. No! I mean, I solved it via the trig and it came out with a messy 2. Okay, yeah. Let's see. All right. I think we're coming back. Yeah, stream. I think the stream crashed for a second. Okay, so 1 over a cubed, and then here's the relation here we need, so let's just remind ourselves again. We want a tangent, so I'm going to divide by cosine squared on both sides, so I'm going to get tangent squared theta plus 1 is 1 over sine squared, which is cosecant squared. Are we back? I think we're back. Okay, so we're going to use this one on the bottom, tangent squared theta plus 1, right? This is cosecant squared. So cosecant squared u to the 3/2 a secant squared u du. Cosecant squared again, squares cancel, or the over 2 cancels. How does this simplify? So we have 3 signs on the bottom. Oh yeah, now it's pretty messy. Yeah, so the a's cancel. What do we think, guys? So we have 1 over a squared, 1 over cosecant of u cubed, times secant squared u. So we basically have, yeah, 3 sines on the top, 2 cosines on the bottom. Okay. We're getting somewhere. So 3 sines on top, 2 cosines on the bottom. Or no, am I saying? Yeah. 3 sines on top, 2 cosines on the bottom. So it's basically tan squared times sine of u. I think that's it. Is this the mess that you were talking about in the chat? Does this have a nice solution? I'm not even sure. Yeah, and then we still have to do the same type of plug-in at the end, so it's going to be messy either way. You could probably do it the other way too. You just need to know your hyperbolic trig relations, which is, I think, the harder part. If you do it this way, then you just need to know the regular trig relations, which I think is maybe easier to remember. But then you need to solve this integral, which is like a little bit annoying. But I think it can be done. Yeah, this is actually even worse than the other one, right? You guys love giving me these hard problems. Nah, I used x over a equals tan u. Okay. Yeah, but I mean, we would need to solve this integral first, right? And got at the end a squared plus sine. Yeah. Oh, are you talking about the... Oh, okay. Tan u. Oh, wait. X over a is tan u. Are you talking about at the beginning? X over a is tan u. Yeah, that's what we have here. Yeah. Okay, yeah, how did you get to the end, though? So you solved this antiderivative? Okay, we'll get to it, Jake. Other Jake. We got 2 Jakes. Tangent squared u sine u. I mean, does this have a nice one in the... Can we look this one up in the back of the book? Does this have a nice antiderivative? I can't remember. It doesn't look like any of the ones I remember. It looks like the ones that you might need to do, like the repeated, like by parts or something. But, or maybe this one is in the calculus book. Okay, so you're saying you got this, what, you looked this up in the calculus book or something? So you're saying the antiderivative is a to the negative 2 times sine. So you're just saying that the antiderivative here is sine, though? Did I do something wrong here? I feel like I simplified this correctly, right? 3 sines on top, 2 cosines on the bottom. Yeah, it's just tan squared sine u. So the wave is saying that he just got a to the negative 2 times sine of u plus c, but well, what was different about it, though? Because all I did was replace this with this squared, and then I think this is good, but then the antiderivative of this is not sine, so I'm not sure how you just got sine. Sine u. Yeah, if it's just sine u, then great. But oh, okay. Wait, is this secant squared on the bottom though? Then it would be easy. But no, I don't. That wouldn't make sense. Should be cosecant, right? Yeah, we just did it right here. Oh wait, no, I divided by cosine. So this is secant squared, right? This is wrong. Right? Divide by cosine. Yeah, I had these mixed up. My bad. Oops. This is secant squared to the 3 halves. Okay, so now the squares cancel here. Secant u cubed, secant squared, so it's just secant on the bottom. And 1 over secant is obviously just cosine. Okay, now we're good. Thank you. I think it did. Yeah, I can't see in this new chat, Zach. I'm trying the restreaming on YouTube and Twitch now, but the chat that it gives me in OBS, I can't really. It's not giving me any raid information or anything like that. So maybe I'll need it open in the other window in just the normal like Twitch studio thing to get more information. But welcome. We're working on these weird integrals here. First we did a hyperbolic substitution and we got a really weird answer. Now we're doing a trig substitution and getting a little bit of a better answer. So looks like we got 1 over a squared. This is going to be sine u, not sun. Sine u plus c, some constant. And then we're going to have to replace u with the arctan of x over a. So this is really arctan of x over a. We'll see. Okay, and then here's the part where we want to know what the sine of the arctan of x over a is. X over a, arctan. This is some angle theta, such that the tangent of it is x over a. So this could be x, this could be a. And then this would be square root of x squared plus a squared. So the sine of this angle will be, now I'm mixing this over this, right? Opposite over hypotenuse, I think, right? Yeah. So that sine should be x over square root of x squared plus a squared. I think that's right. And then that should be the final answer. So just replace sine of arctan of x over a with x over square root x squared plus a squared, and then assuming I didn't do anything wrong. No, we're doing 2 hours today, Jeff. Not 20, just the regular 6 hours. Yeah. Okay, so are we good on this one? So basically just replace this weird composition of a sine and an inverse trig function with this information in the triangle. We know that the sine is the opposite angle over, or the opposite side, the ratio of the opposite side over this hypotenuse. That's this. So just replace this with that. That should be the final answer. Or you could probably do it that hyperbolic trig way, but then at the end you're going to need to know your hyperbolic Pythagorean theorem basically, or some sort of hyperbolic version of this triangle I drew in order to figure out what the like hyperbolic sine of the arc hyperbolic tangent or whatever the other thing was. Wait, how did you do that triangle thing? So the triangle thing is just to remind us that this sine of this angle, the arctan of x over a is some angle whose tangent is x over a. So the angle whose theta is the arctan tangent to the negative 1 over x over a of x over a. This angle here is the angle of a right triangle such that the opposite angle is x and the adjacent angle is a. The proportion is x over a. And then in a triangle like this, the hypotenuse is going to have value square root of x squared plus a squared. And so then we know that the sine of this angle is x over this hypotenuse value. Yeah, we're open to questions from chat. Did we have any other ones, though? I think, what was the one we were asked about before? Just looking at the chat here. Math Heart. I'll be back at 5:30. Yay, Raid. The big man is blind. Sensei, check his work. 24-hour stream. How did you do the triangle thing? 2 hours isn't bad. Open to questions from chat. Yes. It is the final answer. Yeah. Okay. I think we're good. So what should we go on to next? I'm not sure what if we had any plans for the next question yet. Yeah, I think we're good here. We solved it basically the wrong way, or it was probably right, but hard to get to the full solution without having some weird composition of hyperbolic trig functions and inverse hyperbolic trig functions. But I think we eventually figured it out a good form for the solution. Jeff's got a word problem here. That's not I'm already scared. Earth is 93 million miles from the sun with an orbital period of 1 year. Mercury is 36 million miles from the sun with an orbital period of 88 days. How would you compute the average distance between Earth and Mercury? Okay, I'm assuming that... Are we assuming these are circular paths? Orbital period of 1 year. Okay, I can think about this. This is interesting. Okay, so I'm guessing we're assuming they're circular paths or something, or else it's probably way harder. Earth is 93 million miles from the sun. Okay, so here's Earth. E to the 2I pi says hyperbolic cosine of x squared minus hyperbolic sine of x squared is 1. Yeah. We were doing it that way, and then we got a weird answer at the end, but it was probably still correct. It was just just some very weird answer. So that's the relation we used at the beginning, and then we ended up changing it to just a normal trig substitution because it gave us a simpler solution. Okay, just trying to sneak in some spherical geometry. Circular is fine. Yeah. Okay, yeah, without circular, this is going to be a lot harder. So Mercury is 36 million miles, orbital period of 88 days. Okay, so this is a 1 year orbit, and then I guess I'll do the other one in a different color. So then we have an 36 million miles. And I don't know why I did Mercury blue. Well, I guess the Earth can be green, that's fine. Yeah, Earth is green, Mercury blue, 36 million miles, 96, so I guess the sun here is in the middle. In this picture, but of course, they're orbiting, and it's very much not to scale. 88 days is the orbital period for the other one. And 1 year. Okay, and so what else do we need to know about the problem? Is there anything else? So how would you compute the average distance between Earth and Mercury? Does it matter like which direction they're going? Probably not, I guess, right? Oh, we need to do some sort of integral here. Okay. Do we know what the starting locations are? I guess that doesn't matter, right? Maybe. No, we just need integral over all their paths, the distance between them, and then we'll take the average, I guess. I need to think about the time lengths. Like, do we integrate over 1 year for the Earth and then check what the average distance is over like 1 year of the Earth moving? Because then Mercury's going to go around multiple times for every time we do one Earth year, right? There'll be like, 4 of these or something. 4 years for Mercury. Okay, yeah, so I'm just thinking about the problem. One more thing, generalize for any 2 planets. Okay. Yeah, we can think about it, the generalization for any 2 planets as well. You have them drawn at their maximum distance. Cool, yeah. They orbit in the same direction. Okay, so they're orbiting like in the same direction here. Let's assume that. They might be at this distance, but I guess theoretically they could always be, maybe they'll never reach like perfect. Well, yeah, at some point they'll be horizontal, right? Yeah. No matter where they start, at some point they'll be, horizontal. Unless they're going like the exact same speed, but they're not. Jeff says the problem is that Mercury is going to catch up with the Earth in less than a year. Yeah, I think that's when the orbit repeats. We can start them lined up at 0 degrees, but it shouldn't matter since we're taking an average. Yeah, but are we taking an average over like one Earth path? Is that what we're saying? Like, so like, let time go. Let time start moving. Let the Earth start moving around. Once it gets like one full rotation, we can look at the distance at every point, and then we want to know what's the average of that distance over the one Earth rotation, or I'm not sure what the problem is. That correct? Yeah, we'll assume the orbits are planar, sure. So yeah, let's just write down what we think the problem is. So we want to know what's the average distance between Earth and Mercury. And then my question would be, is this the average distance between Earth and Mercury during one full Earth orbit? Or maybe it doesn't matter. I'm not sure. Oh, so average over all time. Okay, so this is like an infinite integral then? So like from negative infinity to infinity and just let it go? Maybe, yeah, that, okay. I think the path repeats. Okay, so the distance function is periodic, sure. Oh, okay. So probably then just like an average. Okay, so I think what we're probably going to end up calculating is integral from negative infinity to infinity. And then we can start them basically wherever we want because we're just going infinitely in each direction. And then we can just look at this distance function. So it's going to be the distance from the sun to the Earth. Or sorry, not the sun. The distance from Mercury to Earth. And this is obviously like, this is going to be a function of time, right? So this is a distance function as a function of time. And it's going to be dt. sorry, average. So we're going to be, actually, I guess, yeah, maybe we need to take some limit here, possibly. So it's going to be like from negative n over 2 to n over 2, and then we're going to need to divide by n over here to take an average. And then take a limit, maybe, n goes to infinity. So this would be the average over some, distance around the origin of size n, and then we're just going to let n go to infinity, I guess. I don't know. You tell me, Jeff, is this... Oh, okay, yeah, I'm looking at your chat now. The average as t goes to infinity, it's an average, not a total. Average over one period should do it. Then got stuck. Okay, average over one period should do it. Yeah, it should be the same. This should be the same thing as the average over one period, right? Yeah. But yeah, I'm still confused. Is this the average over one period for either of them? I guess for the Earth, right? Because that covers all the... Yeah, and then it'll just... Well, actually... Yeah, can you just take one period? I'm not sure if that... Is that the same thing as this? I don't know. So I guess first we want to figure out what we're trying to solve. Is it this limit, or is it just the average over one period? And then if it's the average over one period, the one period of which orbit? I would think it would be the Earth, right? Since we don't get a full orbit for the Earth out of one orbit for Mercury. So yeah, once we figure that out, then we can start trying to figure out what the solution is, but it's probably going to be a little bit messy because I know these distance formula integrals are not usually nice. It might end up being like another one of those trig substitutions like we were just doing for the other one. Because, distance formula is going to have like, square root of, some difference squared plus some other difference squared, so... I feel like it does matter where they start though, right? Because if we're going to just look at one full Earth orbit, it's... The average distance is going to depend on... maybe we need to do an integer orbit number for both of them. But then they would have to be like some rational, angle away from each other to begin with or something. If you plot the distance function, you'll see it's periodic, but not 1 year or 88 years. That's what I was just saying, yeah. But it depends on where they start, right? They need to start at like some sort of rational angle relative to each other, or else it's actually never going to repeat. So I would actually say your problem's actually kind of ill-specified unless we can really figure out if there is a periodic orbit, and there's only a periodic orbit if and only if, like I was saying, these differ by some rational angle. So yeah, if they start out completely opposite to each other, then they're probably fine. Actually, yeah, it also depends on the 80, 88, and 1. Okay, yeah, these divide each other, I guess. So then you're probably... Oh, wait, yeah. No, we need to figure out... These probably don't even perfectly divide each other, because 1 year is like 365.24 days or whatever, and this isn't going to go into that perfectly, so... Yeah, I think this is technically the answer, unless you can prove that the total system is periodic, which would be if their angle was rational. But otherwise, you would have to do this, because if this isn't periodic, then maybe there's like some limiting formula, but this is getting into like ergodics and stuff. So now it's like, yeah. Start with Sun, Mercury, Earth. Okay. No, it'll repeat for sure. How do you know it'll repeat for sure? Well, if I start them at both at 0 degrees. Okay, yeah, then they're probably, then they're a rational angle from each other. Yeah, because 0 is rational, sure. You can parameterize Mercury as 36 times cosine something, 36 times sine something. Yep, yeah, that looks right. So it's periodic. Okay, so Jeff is suggesting we just start them like together and then they just start moving. Okay, yeah. So then what would the period length be? I guess that's like a separate math question, right? How long? So if we start them together, how long would it take for them to go all the way around and then meet at the same point again at this exact point? So like they'll be moving at two different speeds, right? Like one's going faster, but they'll eventually like kind of lap each other enough times and then they'll meet back up. At this point, it could just take like a really long time, I guess, depending on what the relative speeds are of each of them. Oh, yeah, I guess there's some dropped frames. Should be coming back. The planets must catch up because there are only two of them. Yeah, it'll catch up, but we don't know if they catch up and meet back at the exact same point here. That's the problem. Okay, yeah, the internet's just catch up. Mercury completes an orbit, it will catch up with Earth. Yeah, that's true. But like I was saying, yeah, it might just not catch up like at this exact point in the future, or not for many rotations possibly. All right, I think I'm not sure if this. All right, I'm trying to get the stream back up. Trying to solve this streaming issue. It's really annoying. But yeah, we got about 30 minutes left. All right, I'm gonna have to shut down and start back up. Quick, let me try that. And now OBS freezes. Great. Sick.
Hell yeah. Hell yeah.
So annoying. How does it just crash? And what, am I going to lose my recording now? Great. So annoying. This is so stupid. Yeah, it's still frozen. It won't do anything. What the fuck? Why is it frozen though? What the I can't even close it. So dumb. Great. Software is so terrible. What the fuck? This is just gonna lose this fucking. Go crazy. Fucking hate OBS. What the fuck? I can't do anything. It literally doesn't work.